This video is a tutorial on how to find the responses of first-order systems with Laplace methods. Now, we should remind students, as with many of the other videos, that these are meant to be tutorial questions for students to attempt by themselves, and therefore it's important that after you've read the question you pause the video and try the question yourself before you look at the answers, otherwise you will get very little benefit. Now, reminder at the bottom of the key formula we're using, that the Laplace of a derivative is s times the Laplace of the original signal minus the initial condition. In some questions we will ignore the initial conditions and others we won't. First question then. You're given two systems here represented by first order differential equations, and in both cases we're going to assume that the input u is a unit step. What we'd like you to do is derive the responses for w and x using Laplace methods and assuming zero initial conditions. So now is the time for you to press the pause button and try this, because I'm now going to continue and look at the solutions. First model then. Now I'm going to derive the Laplace very quickly because that was covered in the previous tutorial. So we have s plus 4 into w equals 3 over s, or w equals 3 over s plus 4. You'll remember we were told ignore initial conditions. So having got the Laplace transform representation of w of s, I can now use partial fractions and write w equals a over s plus b over s plus 4. Now this is a straightforward transform, so I can use the cover-up rule. So in order to get a, I'm going to set s equal to 0, cover up the s, and I get 3 over 4, so that gives me 0.75 over s. And in order to get to the b, I set s equal to minus 4, cover up the s plus 4, and you'll see I get minus 0.75. So there's our partial fractions, and in consequence w of t equals 0.75 minus 0.75 e to the minus 4t. Next example then, we have 0.2 dx dt plus 0.04x equals 1.2u. So again, I'll do the Laplace quickly, because that's something you should be familiar with by now. So 0.2s plus 0.04x equals 1.2 over s, because again we said that u was a unit step, or x equals 1.2 over 0.2s plus 0.04 all into s, or 6 over s plus 2 into s. Now, as normal, I can treat this as partial fractions, so I get x equals a over s plus b over s plus 2. Sorry, if I should have a 0.2 there, I do apologise. We mustn't miss these important details. So again, I can use partial fractions. So if I set s equal to 0 and cover the s, I get 6 over 0.2, which is 30. So I get 30 over s. And in order to get the b, if I set s equal to minus 0.2, cover over the s plus 0.2, then I'm going to get minus 30. So you get your partial fractions 30 over s minus 30 over s plus 0.2. And now I can use my table to do the inverse Laplace, which gives me x of t equals 30 minus 30 e to the minus 0.2t. Next question set then. You'll notice the difference here from the previous question set is minimal, but we've introduced an initial condition. So the question is, can you still use Laplace methods and deal with this initial condition? So again, now's the time to pause before I go through the solutions. So the first one, I'm going to write the Laplace transforms straight down as normal. So we've got 0.5s plus 1 into w of s minus 0.5 w of 0 equals 0.33 over s. And if I rearrange this, I'm going to have 0.5 s plus 1 w equals 0.33 over s plus 0.5 w of 0. And now I can move the 0.5 s plus 1 to the other side. So I get w equals 0.33 over 0.5 s plus 1 times s plus 0.5 w of 0 over 0.5 s plus 1. And then the final step is to try and put these denominators in monic form, because that makes life much easier. So if I multiply top and bottom by 2, I get 0.66 over s plus 2 into s plus w of 0 over s plus 2. Now you'll notice, I'll circle it here, that one of the terms we've got has 2 poles in the denominator. So we need to use partial fractions on that to separate it out. So I'm going to write this now as a over s plus 2 plus b over s plus w of 0 over s plus 2, and we need to get a and b. So in order to get a, I need to set s equal to minus 2, cover up the s plus 2, and so you're going to get minus 0.33. And in order to get the b, I set s equal to 0, cover up the s, and I get plus 0.33. So what you end up with is 0.33 over s minus 0.33 over s plus 2 plus w of 0 over s plus 2. And you'll notice we get the classic sort of solution here, which I'll write down at the bottom, that therefore w of t equals 0.33, and then we get plus w of 0 minus 0.33 into e to the minus 2t. Next one then. So 15 dx dt plus 25x equals 5u, and x of 0 equals 4. So again we'll use this same technique as normal. 15s plus 25 into x minus 15x of 0 equals 5 over s. Now I'm going to reduce myself a little bit of stress here by dividing through by 15 straight away. So I get s plus 5 over 3 into x minus x of 0 equals a third over s. And now I can divide through by the s plus 5 over 3 and move the x of 0 to the other side. So I get x equals a third over s plus 5 over 3 plus x of 0 over s plus 5 over 3. So again you'll notice that we've got a term here which has got a quadratic denominator, and so that particular term we're going to need to use partial fractions to put it into the forms that are in the table. The term over here is already in the form of the table, so we don't need to do any more with it. So I can write x equals a over s plus b over s plus 5 over 3 plus x of 0 over s plus 5 over 3. Now, in order to get a, I need to set s equal to 0 and cover over the s, so we get 1/3 over 5/3, which is a fifth, so you get 0.2 over s. In order to get the b, I need to set the s equal to minus 5/3 and cover the s plus 5 over 3, and so you're going to end up with minus 0.2 over s plus 5 over 3, and hopefully you'll again see that this solution takes the classic form. So if I write it over here, I've now got x of t equals 0.2 plus x of 0 minus 0.2 into e to the minus 5 over 3 t. Next questions then. Use Laplace methods to find the unit step response of the following first order systems. And you'll notice I've listed 6 possible systems here because you never know which ones might come up in an exam, and indeed there might be a few others that you need to cover. Now if you're not familiar or up to date with these, look at the videos on modelling, make sure you know how to derive the corresponding models. We're only going to give the answer for one of these because all the others follow the same syntax, the same concepts, so if you can do one, you should be able to do them all. So now's the time to pause if you've not tried these before we continue. Here's a question. I've got the mass damper system, m dv dt plus bv equals f, and I've got an initial condition v of 0 equals v subscript 0. And I want to solve for the velocity. And you'll notice I've not put numbers in because you can actually solve this one entirely algebraically. So let's do that. If we take Laplace, we get Sm plus b into v minus v0 equals, now we're assuming f is a unit step, so I'm going to put f equals 1 over s. If I now rearrange this, I get Sm plus b into v equals 1 over s plus v0, or v equals 1 over s, Sm plus b. I forgot an m here, I do apologise, there should be an m on that v0, let's put it in, and then we get plus m v0 over Sm plus b, and finally, putting the denominator into monic form, I get v equals 1 over m over s plus b over m plus v0 over s plus b over m. And you'll notice this is just like the questions we did earlier in this video. So now I want to separate out this bit which has got a quadratic denominator into simple forms that we find in the table. This one over here, I don't need to do anything with it because it's already in the requisite form. So if I do partial fractions, and I'm going to do this one by inspection because you should be getting better at that by now, I've got something over s and something over s plus b over m, because those are the two factors in the denominator. To find out what goes over s, I set s equal to 0 and cross the s in this thing I've marked in the red circle. So what do you get left? You get left 1 over m divided by b over m, which is 1 over b. So that's that residue. Now I happen to know, because I've been doing lots of these, that in a consequence this other residue is going to be minus 1 over b, but you might like to prove that to yourself if you're not convinced. So here's my total partial fraction expressed in the form, or the forms that are in the table. So now I can write down the answer at the bottom that v of t is going to be 1 over b plus v0 minus 1 over b into e to the minus b over mt. Finally, we've got some questions which look at more involved input signals. What if u of t is not a step, but it's a different sort of signal, and we may or may not have 0 initial condition. So you'll see I've taken the input for this one to be e to the minus 3t, or the input for this one to be sine 2t. So can I use Laplace to deal with these? Is it straightforward or not? Now's the time to pause, try these questions by yourself, and then look at the solutions in a moment. First one then, so I've got 0.5 times dw dt plus w equals 0.33 times u. So what am I going to do? First I'll take Laplace as ever, and I'm going to get 0.5 s plus 1 into w equals 0.33. Now I know the Laplace of this u of t, it's 1 over s plus 3, so I'm going to put that straight in. And you remember, for this particular case, we had an initial condition, w of 0 equals 0, so I have not included the initial condition. Now I can divide throughout, so I get w equals 0.33 over 0.5s plus 1 into s plus 3, or putting all the factors in monic form because it makes my life easier. I multiply through by 2 and I get 0.66 over s plus 2 s plus 3. So consequently I can write w in partial fractions again. I can write it as something over s plus 2 and something over s plus 3. So what's the something over s plus 2? Well, we're going to cover over the s plus 2, set s equal to minus 2, and you'll see, what do we get? We get 0.66 over minus 2 plus 3, which is 0.66. In order to get the residue of the s plus 3, I'm going to cover the s plus 3, set s equal to minus 3, so I get 0.66 over minus 3 plus 2, which is minus 0.66. So in consequence, I've now solved Wt equals 0.66 into e to the minus 2t minus e to the minus 3t. Now, for this final example, I'm just going to have to jump back because I think I've missed a piece of information. There it was. We didn't write that down. X of 0 equals 4. So let's just add that on so we don't forget it. So for this one, we've got a slightly nasty looking input. U is a sinusoid, but that's quite common. You might want to do frequency response. We've got an initial condition of 4, just to be awkward. So how might we go about solving this one? So again, we take Laplace as ever, 15s plus 25 into x of s minus 15 times 4, so that's 15 times the initial condition, equals 5 times 2 over s squared plus 2 squared. So you'll remember that the Laplace transform of sine 2t is 2 over s squared plus 2 squared. Now what I can do is I can rearrange this by putting x on its own, and what have I got? I've got 10 over 15s plus 25 into s squared plus 2 squared, and I've also got plus 60 over 15s plus 25. So you'll see I've moved the 60 from the left hand side to the right hand side and then divided through by this simple factor. Next, I want to make sure that all the denominators are expressed in monic form, so I'm going to divide through by 15. So I get 2/3 over s plus 5 over 3 into s squared plus 2 squared, and then I'm going to get plus 4 over s plus 5 over 3. Now first of all, we perhaps don't need to bother about this term on the right much more, because that's simple. You can deal with that. You can see straight away it's a simple exponential, and so the initial condition is only affected by the dynamics of the system. It's got simple first order dynamics. You're going to get that simple exponential out. But the other term, the dynamics of the input, also affect the behaviours. So you'll see we've got something which has got the dynamics of the model from the s plus 5 over 3 and the dynamics of the input from the s squared plus 2 squared. And for this one, we're going to have to use more classical inverse Laplace methods and partial fractions. So I can write this down. I'll put it underneath. It's going to be a over s plus 5 over 3 plus bs plus 2c over s squared plus 2 squared. So you remember, I know that in the solution there could be components of cos 2t and components of sine 2t. So I've put in this partial fractions. The cos is the bs over s squared plus 2 squared, and the sine is the 2c over s squared plus 2 squared. Now, how do I find these unknown residues? The a is straightforward. I can use the cover-up rule in order to get the a, because it's a simple factor. So in order to get a, I'm going to set s equal to minus 5 over 3, and cover up the s plus 5 over 3. So what do you get? You get a equals 2/3 divided by 25 over 9 plus 4. And you say, well, yeah, it's okay, I can do it, but it's not particularly nice. That's fine, but that's good enough for what we're doing here. In order to get the b and the c, we need to expand up. So we need to write a into s squared plus 2 squared plus bs plus 2c into s plus 5 over 3, and I've run out of space, so I'll have to squeeze it in here. What does that equal? It equals the denominator, which was 2/3. So that's my expansion. We'll try and keep that separated. So having done that, can I now solve for b and c? Well, fairly clearly, equating coefficients of x squared, I get 0 equals a plus b. I already know a, and therefore I can get b. If I do constants, so s to the power 0, I get 2/3 equals 4a plus 10c over 3. So again, I've already got a, so I can solve for c. And the final solution, I recognise this a over s plus 5/3. That's easy from the table, it's an exponential. And I also recognise the other two terms. The bs over s squared plus 2 squared tells me I've got a b cos 2t, and the other one I've got a c sine 2t. So in conclusion, we've given a short tutorial sheet on deriving responses for first order ODEs using Laplace methods.